and good morning from my side. I'm going to talk about the HoWa-PRO project, which lasted for the last almost 2.5 years at the German Weather Service and other partners. And I will talk a lot about weather radar adjustment with commercial microwave links and some experiments without commercial microwave links. As a quick motivation, I want to show you the areal event, large flooding in Western Germany, also in Belgium in July 2021. And here I have a 3-day rainfall sum over the region of Western Germany. Here's Rhineland-Palatinate. And you see the rainfall map from the radar, raw radar here, and gauge-adjusted radar here. And as a reference, daily rain gauges, which are not used for the adjustment here, but they're just used for reference. And you can see that we have in the raw radar quite underestimation of roughly 50%. And in the gauge-adjusted radar, this underestimation is reduced, but still we have some underestimation. And that is one of the reasons for our motivations for our project, HoWa-PRO, which is based with 4 project partners: German Met Service, University of Augsburg, Technical University of Dresden, as well as flood forecasting agency from Saxony and a company from Saxony. And we will look mostly at the first part about improved QPE from radar CML merging, which in the project is then used in a hydrological ensemble forecasting, where I also want to show 1 or 2 slides in the end. And those hydrological forecasts then are used for probabilistic warning at the local scale in Saxony. That too is the part for the project. And now I want to very briefly introduce commercial microwave links. You probably all know that they are backbone of global mobile communication network, and rainfall strongly attenuates the transmitted signal. And if we measure the difference between transmitted and received signal levels, we can calculate back to the rainfall along the path. There's a quite nice relationship between the attenuation and the signal and the rainfall, which allows us to calculate this. But as most of you know this, I will quickly jump over how this can look like for whole Germany. Here's a comparison we did for some years ago between Radulan RW, gauge-adjusted radar product, and CML interpolated map. We'll talk about the processing in a bit. And you can see that in general, you have a nice correspondence between the 2 maps, which was a further motivation for us to use the CMLs for the adjustment. So going a bit more to the details, how did we do the CML processing now within this HoWa-PRO project? On the right side, you can see the result. It's a comparison of 60-minute rainfall sums from the CMLs and the gauge-adjusted radar. And you see quite a good resemblance, but of course also some differences. In the end, we want to improve this product by using this data. So what we did is we have a basic set of quality controls, some metadata checks, removal of strong fluctuations based on a rolling standard deviation. So at the moment, nothing fancy there. For the rain event classification, we use radar data. We put a lot of effort in the last years into methods to improve the rain event classification without reference data. But now here we use radar data because we only want to adjust the radar when it sees rain. So that is the reason. And also for a binary classification of rainfall, the radar is quite good. For a baseline, we use the last 5 dry minutes. And for wet antenna attenuation, we use the KR method from Pastorek with some modified parameters compared to their publication. And finally, we also fill some gaps. We interpolate small gaps of up to 5 minutes. And when we detect so-called, what we called it back then, blackout gaps, which is a bit confusing because it could also relate to power outages. But when we have gaps that are based of heavy rainfall that completely attenuates the signal, we also fill those gaps up to a certain length, up to 30 minutes. So that's the specific CML processing here. And now I want to go a step further to the radar adjustment. So what do we do in radar adjustment already now operationally at the Met service? We have the radar beam in a certain distance and we measure rainfall. And within this beam, we also have rain gauges and we adjust the rain rate from the radar to the rain gauges. That is what is right now done operational in a product called, for example, Radolan RW. And now we also have the CML measurements. And what we want to do the same. We want to adjust the radar rainfall to the CML. And to do this, we need a way to compare it. And comparing a point versus the pixel is rather easy. But now we want to compare the line against the radar rainfall. And we do it like this. We have here a rainfall field, locations from CMLs. And we use the path averaged rain rate that is weighted by the length of the intersects for each CML. So we get the path average of all pixels here for each CML. And in the end, we get a path averaged radar QPE. That means for each line, we get the rainfall value of the radar. What you see here, radar at CML. And then we can compare it in a similar manner as the gauges to the radar field and do the adjustment. So we now use CML and radar CML in a similar manner as gauges are used in the Radolan approach, which is the operational gauge adjustment at the German Met service in a tool called pyRADMAN. When you now take this and go back to our example in the beginning as a showcase, we have additionally radar plus CML and radar plus rain gauges plus CML. And what we can see that is the rainfall field is stronger on this side, and also the underestimation is further reduced. When you look at the RMSE here, for this use case, we have the lowest RMSE when we add all information together. So what we did now at the German Met service, we built a software framework to do this not just for a showcase, but to do this in a semi or quasi-operational mode. Because for the duration of the project, we got real-time data flow of CML data from Ericsson in Germany. And the traditional data sources we already have now, rain gauges and radar data. And what is maybe interesting here, we schedule this. We can adjust we can produce products in any temporal resolution we want. So we can trigger this process every 5 minutes, every 10 minutes, every hour. What is interesting here is we have a 48-hour rolling archive for radar and CMLs. So we can always do a nice CML processing using 48 hours of data, which we have here in memory all the time. The processing is then triggered at certain intervals, and we can use pyRADMAN, the approach I showed you, to, for example, produce a radar plus gauge product, or to produce a radar plus CML product. This is built modularly, so we can just add different adjustment methods, any amount of processes or adjustment methods we want. But we can also add different data sources. And what we, for example, plan for the summer is that we include PWS from NetAtmo, a bit more on that later. So we have now this framework, and it was running for roughly 1.5 years now. And one thing I want to add here is the availability of data. The radar composite is produced every 5 minutes, and it's the base for our adjusted products. The rain gauge data comes in at different latencies depending what the source is, from some minutes to up to 20 minutes. when it's stations, rain gauges from neighboring countries, and it takes a bit of time. And the CML data is available after 2 minutes. So this makes a difference in the different products, which we see later. Now coming to some results. We did some experiments with this pyRADMAN framework without CMLs and some. Okay, we did some experiments with and without CMLs. And first to present the ones without CMLs. We played a bit with adjustment methods. So we have this radolan approach, this operational approach, which is a weighted additive and multiplicative adjustment. But we also tested kriging with external drift, where you have the rain gauges, here the dots, and you krig them, and you use the radar field as an external drift variable. And the result can look like this. We also used the approach called conditional merging, which is also kriging based. And what you do is basically you take the rain gauges, do a station kriging, and you take the radar pixels at the stations. So that's the radar pixels. And you do a kriging of those. You subtract the radar field from this radar kriging field and get some kind of noise of the spatial distribution of rainfall, and you add the station krig and this noise from the radar field to a final product. And some results here now. It's just radar plus gauges at the moment. We have an hourly reference rain gauges from partner networks in Germany. We compare the direct pixel above the rain gauge to the grid, and it's for data for 1 month in summer 2023. And we have now here the 3 different methods: radolan, kriging with external drift, and conditional merging. And when we look at the metrics, we get an improvement compared to the unadjusted radar for all 3 methods. Radolan has the best metrics of those 3 products, but when you look at the highest values here during the summer month, we see that the kriging-based methods have a lower underestimation here. So we can also look at this underestimation in a different view. The blue line here is the reference, and the green one is the previous operational radolan RW, and the orange one in both cases is the kriging with external drift and conditional merging. So we can see here also that the highest values are better reproduced by the both kriging methods. So much to this. Coming back to CMLs now, some experiments with CMLs. So we can do the same validation as I showed before, but as for the RTAL event, but now also for a whole month. We use again a direct pixel, but we use a daily reference. Daily here because for the daily stations we have roughly 1,000 distributed over whole Germany, and the hourly stations are roughly 100 distributed over 2 federal states in Germany, Rhineland-Palatinate and Saxony. So here, German-wide scale, unadjusted radar has a larger spread here than the radolan RW, which is produced by pyRADMAN here. We can add the radar plus CML. This has now here a very low latency. The metrics are almost as good, so it's a strong improvement compared to the unadjusted radar, but a strong improvement over the previous product. And we, of course, can add all 3 products together and get nice scores. We get the lowest bias and a low spread here. We, of course, can also look, take this to the hourly reference here. Bit of different kind of evaluation. It's best of 9 pixels. For the same month means we compare the rain gauge, reference rain gauge, to the pixel above the rain gauge and to the 8 neighboring rain gauges, and 8 neighboring pixels, and we use the pixel that fits best. Therefore, the scores are really high here for an hourly basis. And what we see here for this example, it's rain gauges in just 2 federal states, that the radar plus CML product has the highest performance for the whole month. But we also see that all products here have, again, some kind of issue with the highest rainfall values. But overall, we are quite satisfied with the results here for the CMLs. We can also use this pyRADMAN framework not to just evaluate this. We can also go into the depths, for example, of radar parameters. Here, just an example, a varied parameter P, which determines the resistance power within this adjustment steps. And we just can vary it here a bit and do experiments and analyze them. So it's a radar plus gauge here, or radar plus gauge plus CML. And we can optimize it for different kind of events. Coming now to the project again, to HoWa-PRO, where pyRADMAN products are used for seamless hydrological prediction. And this is a slide from Jens from TU Dresden. Thanks for that. They use a different set. They use different products for the seamless forecast. And what they had before the project, you can see in the top row, it's the Radolan RW, the operational system, which is 1 hour resolution, 1 kilometer resolution, updated every 30 minutes with a latency of 26 minutes. Together with a nowcast, Radolan RV, and a forecasting system from ICAN. And that's what you can see on the top row. And now within the HoWa-PRO project, they developed this seamless framework where they use a new product from the German Met Service called Symphony, which is a seamless prediction. It blends nowcasts and the forecast. So this green and blue is combined together in this red forecast. And additionally, they use pyRADMAN, which has a higher update cycle and a higher spatial temporal resolution. We also visualized this within the project, within a demonstrator, which is a web platform. And it's right now done for 3 small catchments in Saxony. And when you scan this QR code, you are sent to this map here, and you have different stream gauges. And in the background field is here the prediction of rainfall, but you can also switch to the measurement, and there the pyRADMAN products are shown. And you can click on this individual gauges and see here this the rainfall in the last 24 hours, the short-term prediction and the long-term prediction of rainfall, and additionally the hydrological ensemble forecast for the future. Most of the times there's nothing happening, because this only runs when there is a forecast for a smaller to big flood. But you can look at this punch card in the archive to check out past events, and then click here and scroll through several events. Now, summarizing all of this, pyRADMAN offers a modular merging framework. And I did not show it explicitly, but it offers products in the same quality as the now operational Radolan RW, but with a bit of lower latency. And the CMLs offer here this low latency, and they can improve the QPE. And as an outlook, we will have a quasi-operational test of pyRADMAN during the summer. That means that we run it as the operational workflow and manage it and look at it like an operational workflow and compare it afterwards to see if we can use it as the new operational workflow within the German Met Service. The CML data acquisition within HoWa-PRO stopped recently, yesterday. And the runtime of the project is also almost over. We collected almost 2 years of data, of CML data now, and now started a market survey to potentially acquire CMLs on a long-term basis. This is pending the decision of the executive board of the German Met Service, of course, but we started the way here. And from July on, we will have a real-time PWS data stream from UMedNet, which we also want to use in this pyRADMAN system. And with that, I want to close. I think we have some time for questions. And of course, the advertisement slide we're showing right now all of the time for the conference on acoustic sensing presentation, which will be our final meeting in June in Offenbach. Thanks.
Thank you very much, Maximilian, for this very nice presentation. Are there any questions to Maximilian from the audience?
There is one in the chat. It's not mine, but
it's Remco's, and I see that Remco is not here anymore. So it is the question and the recommendation also to look into one paper.
Yeah, so within this project, so Remco asked if we systematically investigated radar errors like attenuation, vertical reflectivity profiles, drop size distribution, ZR relations. Within this project, we did not do this. At the Met Service, there is a whole working group that works on also dual pole radar QPE, which is based in the workflow before we start the adjustment. So the workflow is that this radar group does everything from the measurement to the composition of the radar, and then we get the raw unadjusted radar with which I started in the presentation, and we do the adjustment within our group of hydrometeorology. And therefore, no, we did not do here explicit tests, but this is done within German Met Service all the time. To the other question from Alan, yes, the presentation slides will be distributed afterwards, I think.
Hello, I would have one question as well, if I may. I wanted to ask, on the CML you used, were they all on higher frequency? I mean, what was the frequency distribution of the CMLs you used?
So the frequencies were between 10 and 40 gigahertz.
Okay.
With the most CMLs between 20 and 40 gigahertz.
Okay.
So we also know that right now there are for E-band, there are CMLs with higher frequency, 70 and 80 gigahertz, but we have no those high frequency CMLs in our data set right now.
Okay, thank you.
And that's maybe interesting because this relation I showed you in the beginning, I went quickly over it because I thought most of you guys know a lot about CMLs. So this relation here holds pretty well for frequencies 20, 30, 40 gigahertz. For 70, 80 gigahertz, it's not as good, but you can still work quite well with it.
Yeah, and it also depends on the distance of the CML itself, and where the distance is quite long or not. I mean, the path of the CML, was it long? Like a few kilometers, for example?
Yeah. Here you can see a network of CMLs we used at my former employer at KIT, and therefore we can show it. We cannot show the new network here. That's 4,000 CMLs, and the average length is 7 kilometers here.
Okay.
But ranging from 500 meters to 35 kilometers.
Okay, thank you.
I would have a question too. So if you now go for the PWS stations compared to like the CMLs, or not compared, maybe adding it in addition, what do you expect? Do you expect that the CMLs give you a better result than the additional personal weather stations, or is this like just an add-on, an additional element?
That's a bit hard to say. Because we see that CMLs do not always, and for every rain event, add a value. So we also have events where the CMLs, because they are opportunistic, because they have issues, reduce the quality of a local rainfall field. For PWS, it will highly depend on the quality control. And I personally expect that when we do a good job at quality control, we might run in some other issues because of the station density is so big for the PWS compared to the radar grid size at some locations, that we have to try, or that we have to find solutions for that. But in the end, I guess that PWS could offer also quite a large benefit. One of the benefits of the CMLs is that they have this path integration of rainfall, which is close to the spatial integration of the radar. But we just have so many PWS. So for this, now we used roughly 4,000, 5,000 CMLs, depending on the time step. But we will probably get 40 to 45,000 PWS rainfall stations in Germany. So even a factor of 10 compared to the CMLs. And I guess the spatial density can really improve the radar product. So yeah, I'm looking forward to this.
Great. Max, there's another question in the chat. If you experienced a dust event.
So in Germany, most of the times we do not have dust events. Sometimes we have some Saharan dust, but they do not interact here with the density of the dust here. They do not interact with the dust. So we do not see effects here. Depending on where you are, if you are in, I don't know, in the Sahel region in Western Africa and you have really intense dust storms, there could be some issues, yes. But typically there's no interaction between the microwave link and a dust particle, or almost no interaction.
Thank you. It's Karl from the UAE. It was my question. I also was just, I was a little late for the meeting. I was held up somewhere else. So in general, what would be the effect then of heavy dust? Would you get lots of more attenuation? Because we do see it, especially on the velocity field of our radars. For the rest, it was mostly filtered out.
So I would have to look at data back again. We had some data from Burkina Faso, but I think you can separate it nicely because during a rainy season in West Africa, there are not too many dust storms. And when you have dust storms, you're in the dry season. But if it's a really strong dust storm, I could imagine that there will be some attenuation here. But it will, from the signal, it will probably look different to rainfall.
Thanks.
And maybe as Remco, you wrote again, I think. Yeah, we did not do specific experiments. Here, we have a whole radar group within German Met Service who's doing raw radar to the raw radar composite